And yeah, so now it's recording because this dot here is grayed out on this laptop, on this screen, but then it's blacked out on that screen.
Okay, sounds good.
Okay. I think that's about it. So if you can start with the intro about yourself.
Yeah, I can save it.
And then I think at the very end of class I'll make a few announcements and then end the class. So
Okay.
I'll come up after you're done.
Yeah. And I may I probably, well, we'll see. It might not take a full hour and a half. It might
Yeah,
be good.
that's all good. Mm-hmm.
Okay.
Okay, that sounds good.
So how's the, is there, you teach the course with something like, you're currently doing PhD at somewhere else, or
So I'm doing design.
yeah,
Doing working. Let's go for it.
I know that.
Yeah, here's a blog.
I know from the blog.
That's the reason. That's one of the main reasons. But yeah, so I'm down there normally, and I was a student here for undergrad and master's.
That's sweet.
Yeah, and then while I was here, I was involved with the and 100 water first like launching those up.
Yeah.
And so, long story short, I was looking for something this summer, and we want to offer you 100 looking for a summer to offer. And I said, sure, so I'm full.
Nice. So you're involved with the data science division when you were in high school. Cool.
Yeah, I basically just TA for the classes for a while.
Awesome.
You're a student.
Yeah, actually just finished the PhD. So I finished PhD with last one Mike Berg and teaching them and actually midway through the PhD I got super interested in distributed systems. They're all not just a perfect mix for both of those things. So all these like distributed systems experts I've been working with for the past several years. Thanks. Thank you. This all get started. Hey everyone. Does it sound like the mic's working? Okay, great. Cool, well, really nice to meet you. So I'm Robert. I actually just finished my PhD here at Berkeley, so I've been, I started a PhD in machine learning advised by
Michael Jordan, doing more like machine learning theory, so just to say a little bit about myself. And one of the things we encountered over and over while doing machine learning research was that even if you're doing theory or designing algorithms or things like that, you often need to run a lot of experiments to evaluate things empirically. And a lot of people in machine learning end up actually building a lot of doing a lot of lower level systems work, a lot of building distributed systems infrastructure just to run their experiments and just to make things faster and speed things up, because performance is actually a big bottleneck in machine learning. So a lot of the work we ended up doing was really motivated by problems, these like systems challenges we were running in our machine learning research. Really motivated us to start thinking about how to solve some of these distributed systems challenges, how to make it easier to program a cluster or scale from your laptop to a cluster. And so over the past several years, I've been working on distributed systems and actually building an open source project called Ray, which is now starting to gain a lot of traction to make it easy to really scale from your laptop to the cloud. And this talk is about distributed systems and AI because a lot of the interesting research and hard problems in distributed systems right now are motivated by challenges or applications coming from artificial intelligence or data science or machine learning. And so these two topics really go hand in hand. And actually they're starting a lot of, traditionally, so in academia you have conferences about artificial intelligence and you have conferences about systems. And now they're starting to create conferences that are about the intersection of systems and machine learning, which include things like how to build better systems to support machine learning applications or how to use machine learning to improve systems research. And so this is sort of a really active area. All right. So I'll try to, let's see. Oops. OK. So I'll start by painting a picture of what the distributed computing landscape looks like today in the context of the machine learning ecosystem. And I'll try to ground this in concepts you may have learned in this class. So one of the things we're most familiar with in machine learning is the concept of training. That is, fitting a machine learning model to some data. And there are a couple classic examples of this. So one is a classification problem. Taking data points that might be in one class or another, so that might be a binary classification problem where an image is either consists of a dog or does not consist of a dog, or you want to know if it's going to rain or not rain tomorrow, and you have some data and you want to make this prediction, and this amounts to essentially finding lines or finding functions that separate data points of one class from data points of the other class. So this is a classification problem. Regression is sort of the other standard part of the training or classification setup. This is all supervised learning. So this is where you have a bunch of data points, like in the lower left, and you're trying to find the curve that best fits the data. Here we're finding a line that fits the data the best. And when you have a fairly small data set, there are exact formulas for this best fitting line. But as you get larger and larger data sets, the formulas to exactly compute the best fitting line, they're not practical to run in a reasonable amount of time. So what you end up doing is using stochastic gradient descent, which is an algorithm for iteratively taking a new data point. So you essentially, stochastic gradient descent is an algorithm for solving both of these classification problems and these regression problems, where you start with, you randomly guess a solution, and then you iteratively improve it by, so in the case of regression, you want to find the best fitting line. You start with some random line, you take some data points, and you make the line fit those data points a little bit better, and then you take another random subset of the data points, and you iterate this process. And so, this is really the bulk of what has been happening in machine learning in the past, in machine learning research in the past handful of years, where we've gotten really good at taking more problems and fitting them into these classification and regression frameworks, and then solving them with this stochastic gradient descent algorithm. And so this might look very simplistic, this like regression picture or this classification picture, but you can imagine that, so in this xy axis with the regression problem, x might be something, instead of a one-dimensional, just a number, it might be a vector or a large data point like an image. And then the y-axis might be something like, the number of cars in the image. And so you wouldn't plot that on a two-dimensional axis, but conceptually it's the same thing. And now, of course, you're not finding a linear function or a line that fits that data the best. You're instead fitting some high-dimensional, complex function to it, which is people use neural networks for this, which is essentially a family of functions. You can think of it as like a polynomial. And then they use stochastic gradient descent to actually solve these problems. So there are a lot of subtleties in actually getting this to work well, but this picture is representative of a lot of what's happening in machine learning. And you can describe a lot of problems in this way. Okay, so that's the training part. Training is, we often think of it as the main thing, but it's one part of a broader ecosystem. So reinforcement learning is an example of a sort of emerging area in machine learning where you're not just making a single prediction. You're not just taking X and predicting Y, like taking an image and predicting what's in the image. Here you're making a sequence of decisions to try to achieve some outcome. And an example of this is playing a board game like Go, where you're not just really, you can think of it as predicting a move, but that's maybe not the most productive way to think about it. You're really taking a sequence of actions, and you don't really know if each of those individual actions was correct or incorrect. But at the end, you either win or lose. And so you're trying to figure out how to take the sequence of actions or make the sequence of decisions in a way that achieves this outcome at the end. And this is something that machine learning is starting to get really good at. So it also applies to other sequential decision-making things like playing video games. This is Pong. Or you could apply it to learning to control a robot. You can think of walking, like you can think of walking or any kind of robotic control as a problem of making tons and tons of decisions about, what forces or what torques to apply to each of your joints in order to be able to move quickly or to sort of balance and things like that. So this is a simulation of a robot, of a humanoid-like robot. It's very simplistic. Obviously, it's not nearly as complex as an actual human. But it shows some of the basic mechanical forces, and it's essentially learning to run by trial and error. So the first handful of using standard reinforcement learning algorithms, it was able to, after training for a little while, it was able to kind of stumble a little bit, and then after 500 iterations, it sort of exhibits an almost human-like running gait. Here's another example of a reinforcement learning problem. So this might be a bit small to see, but this is a traffic simulation. This is research done by people here at Berkeley. And what's happening, okay, you won't be able to see this, but there are red cars and white cars. And normally so here you have 3 lanes or something like that merging into 2 lanes and then merging into 1 lane. Typically when this kind of thing happens, you end up with like big traffic jams and it doesn't go nearly as quickly as, traffic doesn't go nearly as quickly as it could. If all the cars on the road were autonomous and could coordinate with each other, then you could solve this kind of problem and they could behave optimally. But the question here is, what if some fraction of the cars on the road are autonomous vehicles? So there are some red cars there which are, you can't see, but represent autonomous vehicles. And they're acting individually. They're not actually coordinating with the other cars. And the question is, what can they do to sort of regulate traffic in a way that improves the flow of traffic? So here, they're making decisions about what velocity to go and which lane to be in a way that, and the goal of making all these decisions is to try to make traffic flow faster. So reinforcement learning is perhaps a very general setup for describing problems. It's really describing any setup where you're taking sequences of actions or making sequences of decisions over time to try to achieve some outcome. And if you can describe a problem that way, you can try applying some of these reinforcement learning algorithms. But and then whether it'll work or not is sort of, a work in progress. It's something that's starting to work well, but certainly not for all problems. Okay, so model serving. This is essentially what happens after you train the model. So say you trained a big neural network to translate languages, maybe from English to French. And now you're Google, and you want to use that neural net you trained to actually power a service like Google Search or Google Translate. So you have tons and tons of queries coming in, and you need to sort of evaluate this model and send this response back to the user. So that's the concept of model serving. This typically happens right after you train the model. Okay, hyperparameter search. This is something you may be familiar with in the context of things like the bias variance trade-off. Hyperparameter search, when you're running machine learning experiments, you often have tons and tons of knobs that you have to tune or choices you have to make. Like here's a regression problem. If you're fitting, trying to find the best fitting curve for some data points, you have to make choices like, what kind of curve should I use? Should it be a line? Or here in the middle, this is maybe like a 4th degree polynomial. Or on the right, we have some even higher degree polynomial. And if you make the right choice, it might work really well. And if you make the wrong choice, it might work very poorly. There are other choices, like if you're using some optimization algorithm, what the learning rate for that optimization algorithm is. And so the process of hyperparameter search, essentially searching for the best choices here, that's what hyperparameter search is. And this is a standard thing to do if you're doing training. You're often not just running one training experiment, you're running many training experiments and with different choices and then taking the best one. And it's usually not as simple as just running a bunch and taking the best one. There's a lot of work on different algorithms for intelligently deciding which experiments to stop early on, which ones to invest more resources in, how to choose new experiments to run based on which ones did well and which ones did poorly. So that's a big area. And so data processing. I'm describing all these different components because these are all examples of computational patterns that arise in machine learning which need to be distributed because they're so computationally intensive. So data processing, you probably have heard of MapReduce or Apache Spark or Hadoop. These are standard data tools for processing large data sets. So here with data processing, I'm talking about things like you have a big data set and you want to compute some aggregate statistics of the data set. So maybe you have a bunch of documents and you want to count the number of times that a certain word appears. Or you want to find all the documents, retrieve all the documents that contain a certain word. So that's something that the MapReduce paradigm is set up for. And you have good tools for doing this kind of thing. And here's an example of using a tool like Apache Spark, which is an open source project that was developed here at Berkeley by a bunch of people in the computer science departments, and is now one of probably the standard for processing large data sets. And in this example, the application is you have a bunch of log files, and you want to extract certain keywords from, or find some subset of them that contain some keywords. Okay, and the last part is streaming. So this is actually pretty similar to data processing, but instead of having a big fixed data set in front of you, you have data points coming in one at a time, and then you need to process them, transform them, maybe feed them into some machine learning algorithm, and so on. Okay, so this is a really interesting setup. This is not an exhaustive list, but this consists of a number of important computational patterns in the machine learning ecosystem that people are using all the time today. And one interesting thing is that they're all so computationally intensive. If you're processing data, you're often processing huge data sets. If you're training machine learning models, you need to use tons and tons of machines to do that. If you're doing hyperparameter search, you're often running experiments on many machines. So each of these is implemented as a standalone distributed system. And here are some examples of specific systems. You've probably heard of TensorFlow. Actually, can you raise your hand if you've heard of TensorFlow? Okay, great. So some of you, maybe 2/3. It's a library for specifying functions, like neural networks, essentially, and for automatically computing gradients or derivatives of functions. So this is sort of one of the core primitives used in machine learning. Have you heard of like convex? Can you raise your hand if you've heard of like convex optimization or just regular optimization or gradient descent? Okay, great. So like I mentioned earlier, the core thing happening in training is essentially gradient descent at a large scale, and TensorFlow is an example of a library that makes it possible to do that efficiently. For data processing, you've probably heard of Spark or Hadoop, and there are many examples of standalone, highly engineered distributed systems to make it easy to perform these different computational patterns. Okay, so why are these distributed systems? There are a couple of reasons for this. Why not just run this on your laptop? There are two main reasons. So the first one is just that the second one is actually that the data won't fit on your laptop if you just don't have enough memory or disk space or something like that. So in the end, you need to actually just fit the data, you have to aggregate the memory of many machines together. And the first reason is that even if you could fit the data in memory on your laptop, it would just take far too long. So if you want to run the algorithm in any reasonable amount of time, you're going to end up wanting to divide the work up among multiple machines and execute it more quickly that way. There are actually a number of challenges to using and building distributed systems. So if you want to speed up an algorithm by running it across multiple machines, then someone is going to have to decide what work happens on the first machine, which units of work happen on the second machine, and so on. And that's not something that's easy to do automatically. Either the person who designed the distributed system has to make that choice, or the developer who is building the application on top of that system has to make that choice. But somebody somewhere has to think about how to divide the work up between the different machines. And that's called scheduling, this idea of scheduling different tasks on different machines. And it's far from a straightforward problem. Another problem is just every single one of these distributed systems has to handle failures. What if a machine, if there's a hardware failure or a software failure that causes one of the machines in my cluster to just disappear or to go away? You may think, oh, that's not very common because hardware is very reliable. And that's true in a lot of cases. But at a large scale, failures actually start to become more and more common. And handling failures is actually much more important for reasons other than actual hardware failures. Can you raise your hand if you've heard of Amazon Web Services, like AWS? So if I want to run an algorithm on a large cluster of 100 machines, what I'm going to do is rent those 100 machines from Amazon or Google or someone else. And if I want to, I can get a much better deal. I can get a much lower price for those machines if I'm willing to essentially run the risk that the machines will disappear at any point in time. So essentially, if I can bid some low price for these, what they're called spot instances, and as long as no one is bidding a higher price than me, then I have those machines. But as soon as someone else comes along and bids a higher price, then those machines may be taken away from me and given to the other person. So when a machine is taken away and given to another person, that looks a lot like the machine failing. So handling that scenario is very similar to handling the hardware failure scenario. And this turns out to be very important. You do want to take that approach because then you can actually, it's sometimes like 10 times cheaper to run things that way. Okay, and there are other problems like, some of the machines have CPUs and GPUs, and so that has to be taken into account when you're doing scheduling. You have to communicate efficiently and transfer data efficiently between these machines. So these are all important aspects of what distributed systems have to do. And one of the interesting things is that all of these distributed systems sort of solve the same problems over and over. They're all solving these problems. And anytime someone wants to build a new distributed system because some new computational pattern like reinforcement learning emerges, some new important application, they're going to have to solve these problems over again. This is like the analogy for programming on your laptop. This is like writing programs in assembly or something without an operating system. It's like you're manually thinking about how to manage memory or manage the machine's resources and devices without having the benefit of an operating system that does all that for you. Okay, so there are a number of reasons why this picture that we have today is a problem. One is all these systems are doing tons of redundant work. They're all solving these same problems. So there's an opportunity, so that makes imposes a big barrier to entry if you want to build a new system. And the other problem is that people do need to continue to build new systems because these systems aren't enough, because they're specialized tools that handle these individual workloads. But more and more people are starting to need to run applications or build applications that combine many of these patterns together. So I'll give an example in a handful of slides. But one company that is using Ray, the open source project that we're building, is building an online learning system which streams data in from users, incrementally trains new machine learning models using that data, and then serves recommendations from that model back to the users in this closed loop. And so the way they were originally doing it was they were combining a stream processing system with a training system with a model serving system. So they had to take 3 different systems and sort of try to stitch them together. And that works well on your laptop if you're using Python and you can import pandas and NumPy and all these libraries, and just you can use them together and compose these libraries together to build powerful applications. But in the distributed setting, you have distributed systems instead of libraries. And these things were really not built to compose together. So if you're trying to build applications that combine them together, you're going to have a really hard time. So what we're trying to do, one of the things we're doing with Ray, with this open source project, is trying to get rid of all of these distributed systems, all of these boxes, and instead replace it with a single distributed system underneath, and then sort of reimagine all of these computational patterns, all these functions as libraries on top of a single distributed system. So what this looks like is all of these problems in the red box, scheduling, handling machine failures, thinking about resources like GPUs and CPUs, are solved by Ray, by this single layer down here. And then if you want to build a library for training or reinforcement learning or data processing on top of that, then you don't have to think about those problems, because you almost have this operating system layer which takes care of it for you. Now, this is a picture of what we're moving toward. Not all of these pieces exist today, but a large number of them do. And just to make that a little more explicit, we're starting with this picture on the top. That's what we have today, of a bunch of specialized, special purpose, domain-specific distributed systems. And we're trying to move away from that toward a single general-purpose distributed system with a rich ecosystem of libraries and applications on top. And what that enables you to do, one of the things it enables you to do, is start building applications that compose many of these different patterns together, like libraries. Like the way in Python you can import pandas and NumPy and so on, you could do that in the distributed setting. So for example, if you wanted to build the next Google search engine, you would probably want to import a library for web crawling, one for data processing to take the results of web crawling and to build these search indices. You would want to use a library for training to train models for ranking the different web pages. You would want a serving library for responding to queries from users. And so all of these components need to be distributed. And they all need to play nicely together in a single application. So this picture down here could enable you to build that kind of application pretty quickly. So that's something that will be enabled by moving toward a common runtime. Okay, so if you actually want to achieve this, there are a lot of challenges that have to be solved. And in particular, all of these different computational patterns have very different requirements. Some of them in terms of performance, for example, some of them require very low latency. Some of them require very high throughput. Some of them require certain the ability to handle failures, and others don't. And if you want to have a general purpose distributed system that can support all of these applications, then it needs to be able to support the union of all of their requirements. And that turns out to be a lot of requirements. And so the requirements, if you want to build this, are much more strenuous than building each of these individual ones. Now, I'll explain where this generality comes from, how we are able to design the API to be able to support, implement all of these applications on top. And what the trick is, in all of these distributed systems introduce new core primitives. So for data processing, systems like Spark introduce the core primitive of a data set, which you can transform. And in TensorFlow, the core concept is a neural network, essentially, or a differentiable operator. And like in hyperparameter search, the core concept is an experiment. So all of these systems introduce new concepts. And if the core concept you have is, say, an experiment, it's going to be very hard to do anything other than hyperparameter search with that system. So with Ray, to achieve a general purpose system, we are not introducing new concepts. Instead, we're taking the existing concepts you use to program on your laptop, so functions and classes, and then finding a way to translate those into the distributed setting. So I'll give you an example of that in a second. This is a depiction of a company called Ant Financial, which makes this app called Alipay, which people use to pay for things in China. This is a picture of what the app looks like. Here, this is a picture of a distributed system for online learning, or an application for online learning they built on top of Ray, which isn't so super descriptive, but what happens is you have streaming data coming in at the front. It's being processed by a stream processing library, and then fed into a training library, which is then used to incrementally train new recommendation models. And then recommendations from those models are served back to the user through this serving library. And all of this is built on top of a single framework, and doing so made it much easier for their engineers to learn a single tool and develop, and then made it much faster to run because they didn't have to move data between all these different systems. And so this is an example of the kind of benefit that some companies are seeing using this tool. Okay, so now I'm going to talk a little bit about the API. Actually, before I move on, does anyone have any questions that I can answer? Okay, great. Feel free to raise your hand or stop me if you do have questions. Okay, so here are some examples of regular Python functions. The first one reads an array from some file. I didn't actually include the implementation. And the second one takes two arrays and adds them together using NumPy. So what we can do with Ray is add this ray.remote decorator on top of these functions. And what that does is now when you invoke one of these functions, say you call read array, you have to invoke it with this .remote suffix. And now instead of, normally in Python when you call this function, it would read the array and then return. Here what it does is it immediately returns. And then it'll kick off the computation on a different machine by creating this task that will run somewhere in the cluster in the background. And the result this thing that it returns is this object ID is essentially, if you're familiar with the concept of a future, this is just a reference or an object you can use to eventually retrieve the result of this computation. So because this first function invocation returns immediately, we can call a second one, call it a second time, to kick off a second unit of work that will happen in parallel. Because the first one returned before the actual computation finished, we can kick off 2 of them in parallel. Does that make sense? Can you raise your hand if you've heard of the concept of a future before? Okay. So a future is essentially, it is just an ID which is matched with, which is used, it's like a pointer to the eventual result of the computation. And so, well, let me show the full example. So here when you call ray.get on the ID, that will actually go to the backend, go to the distributed system and say, hey, I have this ID, can you give me the corresponding object? And that will actually retrieve the corresponding result of the computation. So this is useful in the setting where I want to be able to start some computation, but I don't want to, I don't want my Python interpreter to block and just sort of wait for everything to finish because I want to start more things or I want to do something else. So this is like kicking off a thread in the background almost. And then you still have some sort of handle or object you can use to communicate with the thread. So here we were able, the key point is that when you add this decorator, now when you call the function, it just immediately returns, and then it will execute the function in the background asynchronously. So now I can start these 3 tasks. I can just run these 3 lines of code instantaneously, and that'll start this computation. So maybe it would help if I give an example just in Python. Let me try this. Okay, so I'm starting a Python interpreter. Okay, so Ray is a Python library, and I can start Ray. Let's see. Let me just. I have a lot of things running on my laptop right now. Okay, so I started Ray. Now, if you were running, this is all running on my laptop, but if you were running on a cluster instead, this is the only line that would change. You'd have to pass in an IP address here, essentially. Okay, so if I call, if I write a function which just sleeps for 1 second, then normally, if I run this function, it's going to just wait for a second, right? And if I run it 4 times, if I run this function 4 times, then it's going to wait 4 seconds, right? Now, if I add this ray.remote decorator, now if I call f.remote, it's going to return immediately, okay? So it just immediately returned and then started the computation in the background. And what that, now of course, if I want to start another task and get the result, then it's going to take a second. It's actually going to wait for the thing to run. But if I want to do, if I want to do 4 of them in parallel, it's still going to just take 1 second because the 4 calls to f.remote return immediately and start all the 4 different tasks that are running in parallel. And then when they're running in parallel, and then the ray.get call will wait for them to finish and retrieve the results. And because they all happened in parallel, the whole thing will take 1 second. Does this setup make sense? Okay, great. So this is now, so that's sort of the most basic way to take Python, regular Python functions and execute them in the cluster setting or in the distributed setting. But and you know, one thing I didn't show in the sleep example, but tasks can depend on other tasks, right? Sometimes you need to start when you're using functions in Python. you're often composing together, right? You're passing the output of one function as an input into the next function. And so we can do that with these remote functions as well. So that's very powerful, and there are a lot of applications you can build with this tool. But functions themselves are not quite enough for many applications. You often need to encapsulate mutable state inside of classes. And so, the way we do this with Ray is we introduce an actor abstraction. So this essentially is a way of taking Python classes and translating them into the distributed setting. For example, on the left-hand side, these functions don't really have side effects. They don't mutate. They don't change any variables that are shared between all of the tasks. All of the interaction is done by passing stuff in and then returning stuff from the function. But if you have a class and you have some sort of field in the class like self.value, and you want to execute a method on that class, on that object that changes that value, then then the class abstraction is the right way to do that. So here's an example of a simple counter class, which has one method for incrementing a counter. Now, what we can do is we can add this decorator again, and now when we instantiate this class, we create this C object. What that does is it starts a new process, a new service somewhere in the cluster which has a copy of this object. And now when you invoke methods on C, those turn into tasks that are executed on this new service that was started. And you can create multiple copies of this service if you want. So I'll give you an example of how to use this primitive to do distributed training with a parameter server. These two concepts together cover tons and tons of use cases because there's so many applications on your laptop that you can build with functions and classes, and these two concepts let you really translate those into the distributed setting. All right. So let me give you an example of how you can use this API to add a bunch of numbers together. So this is a very simplistic example, and this is not actually something you would do in the distributed setting because it would just fit on your laptop. But say you have these 8 numbers and you want to add them all together. You can imagine instead of 8 numbers, just 1 through 8, you instead have 8 really big vectors. Maybe they represent neural network weights, and you're trying to sum them all together. Then that's something you would do in the distributed setting because your laptop would start to become a bottleneck. Okay, so now say I have this add function with this ray.remote decorator. It's sleeping for half a second just to represent doing half a second's worth of work, and then it adds these 2 numbers together. So how can I add these numbers together? Well, one way to do it is so add only adds 2 things together at a time, and I have 8 things. So I can start by adding the first 2 things together. Then that produces this future, this object ID. Then I can take that object ID and add it to the 3rd number, and that produces a new result. I can add that result to the next number, which produces a new result, and I can continue on in this way until I've added everything together. So how long will this computation take in total? Assuming each add function takes half a second. Anyone want to say it out loud? So there are 7 add tasks because we're adding 8 numbers together. And the interesting thing, well, the unfortunate thing in this case is that we can't run a given add task until it can't execute until it has the result from the previous add task. So all of these 7 tasks have to happen sequentially. And since they each take half a second, we're talking about 3.5 seconds. Okay, so that's actually, there's no parallelism happening here. These are all happening sequentially. All right, but can we do better than this? Well, it turns out we can. what we can do is we can run 4 add tasks in parallel. First, the first one can add the first 2 numbers, the next one can add the second 2 numbers, and so on. Those 4 tasks will all produce 4 results, their own results. And then we can run 2 more add tasks, which execute, add the first 2 results and the next 2 results, which produce 2 more results, and finally add the remaining 2 results together. So how long will this computation take? So these first 4 add tasks can all happen in parallel because there are no dependencies between them. So that stage will take half a second. This next stage will then be able to run in half a second, and then the last stage will be able to run in half a second. So in total, in aggregate, it should take about 1.5 seconds. Okay, so 1.5 seconds versus 3.5 seconds for this one. It's a big difference, and of course, as the number, if you have more than 8 things you're adding together, this difference is only going to get larger. So what this is showing is that it really matters. It can matter a lot how you do it. The first thing you try, may not actually work, right? You may have a big cluster of 100 machines, and you have all these things you're trying to aggregate together, and you write your application, but then it's totally sequential instead of parallel. And changing a handful of lines of code to restructure it to do this instead can make a huge difference. And just to show you what the actual code looks like, these 2 probably look almost identical. At the top, that implements the sequential version, and at the bottom, that implements the parallel version. And really, the only difference is this bottom line, where we have this list of values. We're popping the front 2 off, adding them together, and then appending that new value back to the front. Here we're popping the front 2 off, adding them together, and then appending that new value to the end of the list. So it's a difference of whether we're appending the new value to the end of the list versus the beginning of the list. This is a bit subtle, and it probably is not obvious why that difference gives rise to the difference in behavior. But so that's something that's worth thinking about. But it can be pretty subtle the way you structure your code, how that gives rise to different degrees of parallelism. You guys have any questions about this example or about anything else? Okay. So now I'll talk a little bit about the concept of a parameter server. Can you raise your hand if you've heard of a parameter server before? Okay, great. So this is a concept that's used in machine learning to do distributed training. So so the way that you often architect distributed training applications, you have a number of different worker processes which are spread out on different machines, and they're all computing. Remember, we're running stochastic gradient descent. They're all computing gradients, different gradients. And then what needs to happen is we need to aggregate all those gradients together to update so when I should say, the word parameter here is referring to the parameters or weights of the machine learning model, which may be a neural network. So, for example, if your machine learning model is a linear model, like you're doing linear regression, the parameters are the coefficients of the linear model. If you're using some sort of decision tree or random forest, then the parameters of that model are essentially whatever information is needed to specify the decision tree or specify the random forest. Basically, the parameters are just all the information needed to communicate what the machine learning model is. And in the case of a neural network, those parameters are typically the weights at each layer. Okay, so what can happen in a parameter server is that you need an efficient way to aggregate all the parameters together from a bunch of different worker processes and then broadcast those parameters back out to all the workers. So the parameter server is essentially a running service that has two methods. One for getting the latest parameters. If you're a worker process, you want to get the latest parameters. And one for updating the parameters. If you are a worker and you computed a gradient, and now you want to send that gradient update to the parameter server. So in Python, this is what that parameter server class would look like. And you can add this decorator and spin it up, and now you have a running parameter server. So here's what a worker process could look like. It's a Python function, and it's just looping around forever. It is first getting the latest parameters from the parameter server. So here, PS is a copy of this parameter server object, or a handle to the parameter server object. And we are we're getting the latest parameters from the parameter server. We are computing a gradient update. This is using TensorFlow or something. This is the core part of doing stochastic gradient descent. And then we're sending that gradient update back to the parameter server. So we have this worker process and this parameter server process, and they're communicating together because the worker process is invoking methods on the parameter server. Now, this is, again, so just the way I wrote it here, there's nothing parallel happening. There's nothing distributed really happening. This is all sequential because the worker, the parameter server is not doing anything unless the worker specifically queries it. And when the worker queries it, then it's waiting to get the result. Okay, so if we want to scale this up, we can just create more worker processes, essentially run more copies of this function. And they can all talk to the same parameter server. So now we have a bunch of different workers computing gradients in parallel. Now it's possible that the parameter server might become a bottleneck. So what we can do in that case is just create more copies of it. So start up more copies of the parameter server and then sort of split the different parameters across the different parameter servers. So this is an example of how with relatively few lines of Python code, you can create this distributed training application with a parameter server. This is something that's normally implemented with a big C++ code base, and it's fairly opaque. And here we're able to do it in a handful of lines of Python. So just to show you what that would actually look like in Python, here we can implement the parameter server class. And it's just a regular Python class. And we'll initialize the parameters to be a vector of zeros. And it has a method for getting the latest parameters, which just returns the vector of parameters. And it has a method for updating the parameters, which basically takes in a gradient update and adds those or subtracts those from the current parameters. So now we can actually instantiate this. We can call parameter server.remote. So that starts a new process. And if we want to scale it up more, we can create more copies. And I can call get parameters.remote, which, like before, returns a future. And if you want to actually retrieve the values, you can call ray.get. And then, of course, if you update the parameters and pass in a vector, pass in the update, now when you go back and get the parameters, they'll have changed. So to implement the worker process, we can implement the function and pass in a handle to the parameter server, and then loop around, say, 100 times. And the first thing we're going to do is get the latest parameters. We can actually skip that step. What we want to do is we can compute a gradient update. So here I'm just going to make up an update, but this is normally where you would actually use TensorFlow or actually do the work. And then sleep for half a second to simulate running that computation. And then send the update back to the parameter server. And we'll pass in the gradient. Okay, so now if I start this worker task and pass in the parameter server, and I can start several copies of them. Now if I go back to the parameter server and actually get the parameters, you can see that they're sort of changing under the hood, right? So what's happening is we've started this parameter server, which has methods for getting and updating the parameters. We started 3 workers, which are computing gradients and communicating with that parameter server. And then now we're just letting it run. And so we've basically created this picture in not that many lines of Python. What we've done is we've started all these different services with these Python APIs that can communicate with each other. And you can really start to use these tools to architect distributed systems and build distributed applications. This is something that, without this kind of tool, it's actually quite difficult to do. Okay, so now I will say a bit more about the actual backend and how this works under the hood. So there are here's a depiction of a 3-node cluster. We have 3 machines. Each machine has a bunch of different worker processes. These are essentially Python interpreters that are going to do the work of executing the tasks that we submit. The driver is the equivalent of this is my Python interpreter that's actually kicking off the computation. Each machine has an object store. This is an optimization essentially to allow large objects to be shared between different processes through shared memory without creating extra copies. So this is essentially a performance optimization, but it's very important for a lot of machine learning applications where you have big data sets or big neural network weights that you want to share without creating a lot of redundant copies. Okay. Objects are streamed between machines using this object manager concept, and each machine has a scheduler which is responsible for assigning tasks to different workers or is giving tasks to a different machine. And then lastly, there's essentially a key value store or database which is used to store critical system metadata. So stuff like if a machine fails and we lose a bunch of objects and we need to reconstruct those objects, then the specifications of how to do that are in here. So maybe the tasks we need to rerun to recreate those objects are specified in here. Okay, so now let's go back to this example where we have these 3 tasks that we want to run. How does that actually map onto the back end? Well, here's the computation graph. This is essentially the data structure that the back end reasons about, right? We have these first 2 tasks which can run in parallel, and then the 3rd task which can run once the first 2 have finished. So what we have when we execute this code is all 3 tasks are given to the first scheduler. Then the scheduler will say, okay, I can run the first task. It doesn't really have any dependencies. I can just kick it off right away. And now maybe it'll give the second task to another machine, and that machine will start running, give that task to a worker and start executing those 2 tasks. So now we have these 2 tasks executing in parallel. When they finish, they're going to store their results in their respective object stores. And now this 3rd task is ready to run. So the scheduler can assign it to one of the workers. It needs the outputs from the first 2 tasks, right? So the 3rd task requires the first 2 outputs. So it'll get the first output from the first machine, but the second output needs to be shipped over to the first machine, and then it can be given to the worker. And then this add task will run, and then it'll store its output in the object store. So that's a rough depiction of what's happening under the hood when we're running this code. And some of this metadata, these specifications of how to run the tasks are stored in this database. Okay. So I want to finish by saying that this is an open source project. It's something that's being developed here at Berkeley. And it's something that has a lot of promise in terms of really taking the distributed computing landscape that we have today, which consists of a bunch of special purpose systems, and moving toward a more general way of doing things. And this is something that we think can let people really develop distributed applications at a higher level of abstraction. Not if you're developing an application that needs to run on a cluster, you don't want to have to think about machine failures or scheduling or whatever. You want to be able to just run, code that looks like this, right? Where you're thinking about functions and classes and how to tie those together. And so this is the picture that of what things look like today. This is where we're trying to move toward, where you have a single general purpose system, like an operating system, but for the cloud, that's handling the lower level of all the scheduling and failure handling and things like that. And then we can build higher level applications on top. And then we can compose those applications together or libraries together to build even more things. And so this is something that I think this is what the distributed computing will look like in the future. Distributed computing is becoming more and more important. I would say it's becoming the default for computing. That both because Moore's law is over, individual machines are not getting faster. And also at the same time, tons and tons of data is becoming available. Machine learning applications require tons and tons of computation. So all the trends point toward if you really want to make things faster, you need to scale up your applications with more machines. And now we have the hardware. We can rent hundreds of machines from Amazon, but it's still not easy to write programs that run on those hundreds of machines. And so that's something that I think is a direction that has a lot of potential. Cool. So I'll stop there, and I'll take any questions if there. Yeah. Great. Thanks. Any questions? Yes.
So if I just want to run some operations on Amazon Web Service, what preparation would I have to do before I can use the rate.me vector? Just give an IP address to Amazon, and that's it, or is there more work that has to go into that?
So essentially, what you would need to do, conceptually what you need to do is Ray has a bunch of processes like the scheduler and so on that run on each machine. You would need to run a command like ray starts on each machine to essentially start those processes, and then pass in like one of the IP addresses, and then when you actually are running when you're actually starting Ray with this ray.init command, you would need to pass in the address there essentially, so it can connect to the cluster, and that's about it. Ray also has this autoscaler package, which essentially can take care of launching and scaling clusters on AWS and GCP. So there's actually a lot of good tooling built there. Anything else? Yeah. Yeah, I think so. I would suggest reaching out to the RISE Lab, if you've heard of the RISE Lab at Berkeley, is the main place where a lot of this work is happening. There's the webpage, the RISE Lab webpage, a bunch of professors involved there. You're also welcome to email me, and I can put you in touch with the relevant people. But there are a number of PhD students and undergrads working in the RISE Lab together on these kinds of projects. Yeah. So it is. I think it's a great area to get involved with. Cool. I'll stop there, and I think there's some announcements.